Good afternoon to all of you. Myself, Dr. Javanna Samanta. I teach the digital electronics paper. So one of the most important topic is arithmetic circuits. So basically, all of you know that it is one type of combinational circuit, and you know that combinational circuits are basically that type of circuit where the present state is depends only the present state output. Okay, present state output only depends on the present state inputs. So basically, if you go to the today's all the topics I discuss in this lecture. So basically, introduction, half adder, design of half adder, full adder, design of full adder, replica adders. So arithmetic circuits, you know that basically in this class I discussed the different adder type circuits. Okay, so half adder, full adder, and replica adder, carry save adder. There are a lot of different types of adder circuits are there. So basically, you know that any digital devices like the computer, mobiles, everywhere calculators. So here we can do the different types of mathematical arithmetic operations like the addition, subtraction, multiplication, division, comparison. So different types of circuits. We have to do different types of operation we are performing with the help of this type of circuits in different types of arithmetic circuits. So basically, different types of circuit we are we are the most basically, so the most basic arithmetic operation, that is the ALU, arithmetic logic unit of a computer, performs is the addition of two or more binary numbers. So here basically, if I add two numbers like the first number, that is the addend, and they added with another addend. So basically 4-bit number if I add manually. So if you see that, so basically the first bit, first LSB, least independent bit 10. So it is a basically 2-bit. To simplify this, we need a Harvard. Basically the two data inputs are there. Here basically we are ignoring the carry. So and the next bit, if I LSB plus 1 bit. So if I consider, you will see that 1 plus 0, basically 1 plus 0 means 1. So this 1 and the carry is generating here 0. So that carry is generating 0. So here you can see that this is the 2 data bit. We are adding with some the previous carry. So ultimately 3 bits we are generating. So and we are getting the sum bit as 1 plus 1 0. So carry 1 is generating. So that will propagate to the next bit. So in third stage, you will see that 1 is the carry, 0 data, 1 is the carry. So basically, if we 1 plus 0 plus 1, so that will be equal to 0, and sum is 0, and carry output will be 1, that will propagate to the next stage. So in the fourth stage, that is the MSB, we will see in the fourth position. So you will see that 1 plus 1 plus 1, 1 plus 1 we know that it is sum 0, carry 1, and so and 0 plus 1, that will be sum equal to 1, carry will be 1 also. So ultimately we will find the MSB bit if I add, so this most significant bit we are getting, if I adding 2 4 bits number, so we are getting the sum, final carry is 1 and the sum bit is 1 0 0 1. So the first LSB bit, that is 2 bit, 2 data bit we are adding here basically. So that is the 2 data input A and B, and we are getting the sum and carry output. So basically half adder, this is a digital combinational circuit which can generate the result of the addition of two 1-bit numbers. So result basically we are getting the sum bit as well as the sum bit as well as the carry output bit basically. So these are the basically the very diagram we can do these things. Now if I do the truth table of that half adder, basically these are 2-bit A and B. A, B are both the inputs, and the sum is the output, and the sum bit is the output, and carry output is also the output, 2 output bits. So 2-bit, so 0 0, the 4 combination 0 0 0 1 1 0 and 1 1. So if you see 0 0 for 0 0 AB, so sum bit will be 0 and the carry bit will also be 0. And for 0 1, so sum bit is 1 and carry bit is equal to 0. So for 1 0, sum is 1, carry will be equal to also 0. And for 1 1, sum will be 0 and carry will be 1. So if from the K map, so how we can find the expression for sum and the carry? That is very important. So if we take it two variable K map, one input is A, another input is B. Okay, so that means, so this is 0 1 0 1. So for 0 0 it is 0. For 1 0, that will be equal to, for 1 0 1 0 1 0 it is 1, and for 0 1 0 1 it is 1 also, and it will be 0. So now the two group will get. So what will be the sum expression? So sum expression will be equal to this bit A B bar from this grouping, and from this grouping A bar B. That expression we are getting. So basically this expression A B bar plus A bar B, which is nothing but A XOR B. Okay, what is that input XOR gate? And for the similar way, so from the K map, or if you directly from this truth table, you can also find the expression for carry out. So how we can find this? So all the 3 bits, 3 combinations for AB 0 0 0 1 1 0 1, we have seen that the carry out is 0. So only for 1 1 bit combination, so we are getting the carry out equal to 1. So the carry out expression, carry out will be equal to, simply देखो A and B. So this is the sum expression, sum, which is nothing but 2 input XOR gate, and carry out, carry we are getting AB, carry we are getting AB. Okay, so that is a 2 input AND gate. So if I design this half adder with the help of some basic logic gates, so the diagram we are getting, देखो A B, this is the 2 input, okay, 2 data input, sum we are getting from this XOR gate, 2 input XOR gate, and carry out we are getting this from this NAND, 2 input NAND gate. So basically this is the sum expression we have implemented here, and the carry out we are getting A dot B, that is the 2 input AND gate. Okay, so basic logic gates, with the help of basic logic gates we have designed this the half adder also. Another way you can also, without using the XOR gate, simply basic gates, only the basic gates AND or NOR, we can also implement our half adder. So the sum expression, you will see that A bar B, so this is A bar, this is B and D, so A dot bar B and D, and this one is the A, and this is the, after complementing, we are getting B bar. Okay, so the NOT gate we are using here also, so we are getting A dot B bar, and if I adding it, so A bar B plus A B bar, that we are getting the A XOR B. And in the similar way, carry out we are also getting from A and B. So this is a 2 input AND gate, and we are getting the carry expression. So with the help of only 2 input NAND basic gates, all the basic gates we are designing half adder. Now half adder we can also design with the help of some universal gate NAND 2 or NOT 2. So using the only NAND gates, we can also implement the half adder circuit also. So this is the basically what we are getting here: A bar, B bar, and this is the A. So what we are getting? A dot A bar B bar whole complement we are getting here, and this is B also, so it will be equal to B into so that expression A bar B bar whole complement. So what will be output? Sum. So sum will be equal to A dot A bar B bar whole complement plus B into A bar B. Sorry, this will be A B bar. Okay, so A B bar B into A B and whole complement. Now, if you use the De Morgan's theorem, okay, so De Morgan's theorem, that means so A into A B whole complement double complement dot B into A B complement double complement. So double complement means that will cancel. So A into A B bar into B into A B whole complement. So that we are getting. Now again within that, if I use the De Morgan, so it will be A into A bar plus B bar whole into B into A bar plus B. So now if you multiply this one, so it will be A into A bar plus A B bar, okay, B into A bar plus B into B bar. A into A bar, that is equal to 0, that is equal to 0, okay. So if I complement this one will be, so we will get A B bar plus A bar B. So that is equal to A. We are also getting these things, okay. So and for the carry out we also get this one, okay. So with the help of only for 5 input we are getting the half adder. So 5 NAND to get, we are design a half adder circuit. So now what are the different applications? After basically using arithmetic logic unit of the processor, basically the first जो bit होता है that should be for adding these things, first bit MSB ALSB bit, so that we are using. It is used with the calculator for addition of the numeric address decoding in the processors. Just the different types of. So how we can design this half adder with the help of some half adder description language. Most you know that the Verilog is the most commercial language, HDL language. We basically use this Verilog. So industry people they use this. So we can use the module, half adder, and structureless type modeling. So that will be the structureless type modeling, and we can also that from the logic design we can easily get the structure. And using the behavioral modeling simply by using the A is equal to A XOR B, C equal to A and B, we can get the half adder in from the Verilog circuits. Okay, for full adder basically if we see in the first slide, second slide. Okay, so that second and onward bits we are getting the two data bits and one carry previous carry. So for that type of addition we need a full adder circuit. So basically AB got the data input and the C is the previous carry. So ultimately we are getting the sum as well as the carry bit. So it is also known as the one bit full adder also. So one bit full adder or basically one bit. 1 bit full adder, 1 bit full adder, 1 bit full adder. So in the similar way, from the K map, if I find the truth table, if we so the truth table, so from that, so 3 input, 3 zeros to 3 1, and we are getting the carry expression as well as the sum expression. So in the similar way, if you so sum expression, sum will be equal to देखो a bar, okay, a bar, b bar, c plus 4 expression. So that is a bar, b bar, c, a bar, b, c bar, then a, b bar, c bar, and this is abc. From that 3 expression, so sum expression will be a XOR b XOR c. So basically it is a 3 input XOR gate. So we are getting the 3 input XOR gate. From the K map we can put this, that expression we can get. And in the for the similarly for the carry out we can also put this all the where it is high. So that position we have to place in the K map, and from that C we are getting A B plus BC plus AC. So that if I design, so basically it is a block diagram. You can see that the two half are there. Okay, so this sum expression and the carry expression, and carry expression you can also modify it in the similar way also. So just using some Boolean expression law, if I use it for the reaction, so my final carry out we are also reduce AB plus C into A plus A XOR B. So that we can also reduce. So how we can implement this full adder with the help of using two half adder circuits. So this is one half adder, and this is its sum expression, this is the carry expression, and another with the help of another two half adder we can also get this and we are getting the sum expression, find the sum expression from here. Yeah, and carry expression we are getting from this C out, where it is basically AB plus C in equal into A into D. So we can also full adder using the full adder, basically full adder circuit using NAND 2 gates only. So this is the one half adder, this is one half adder, and we are getting the C out only using inverse gate full adder circuit. So what are the application? Basically we can use different types of arithmetic circuits, we can use it, or data handling, different types of circuits and parts. Okay, we can also use this type of circuit. And most importantly, counter our full adder circuits, we are basically using counter circuits, where different types of counter, up counter, down counter, okay, decremental counter, okay, so synchronous, asynchronous, different types of counter circuit. We are generally use this type of both half adder and the full adder. And basically multiplexer circuit in communication application, the multiplexer, demultiplexer, we can use this half adder and full adder circuit also. And in memory circuit we can also use this different types of. And basically in processor design, the main important the core of the processor is really arithmetic logic unit. Here we can also use these different types of adder circuit for different types. Okay, so now I also given very long code basically for any type of full adder circuits. Full adder circuit basically, if you see, so we are defined here module. So full adder, this is a keyword module, and within that three input are A, B, C in, and output sum and carry. Okay, so this is a very behavioral style module we are using here. And for assign, sum equal to A XOR B XOR C in, and for carry we can also A and B, or B and C in, or C in and A. So this is the simplest way. We can write here also, there are different styles we can use, the data flow, behavioral and structural. If structural means if your diagram is given in the form of Boolean logic gates, so from the directly from this logic diagram we can also write the Verilog code for the put data also. Here you can see ABC as the input, output, sum and carry. So we are taking some internal connection where we are using here, and here two OR gate, two input OR gates we are getting for so finally sum we are getting from here. And for carry, you can use the 3 AND gate, and finally for carry out, so we are getting this carry out. Okay, so this is the in module. So this is behavioral, behavioral style, and this is the structural style. Structural. So start behavioral means if the expression, output expression are given in the form of Boolean expression, then we can use the Boolean or data flow. And if the diagram is given in terms of the logic gates, so to write that code directly, so we can use the structural style model. Okay, so there are hardware and application hardware and there are bigger adders are a lot of adders are there. So we can for any input numbers, so we can use 4-bit refill carry adder. So the how many numbers, what are the outputs we are getting, what is the size of the truth table, how many functions to be optimized. So depending on that, we can design a bigger adder. So so with the help of this, so this half adder and the full adder are the basic building blocks of any bigger circuit, like repeat carry adder, carry save adder, carry skip adder, carry select adder. There are a lot of research work in this field to design different types of adder circuits. So repeat carry adder, basically you can see that the four, this is the again, and this is the these 2 bits, 4 bits. If we add it, 1 plus 0 1, carry is 0, 0 plus 1, so carry is 0, sum is 1, and 1 plus 1, sum is 0, carry is 1, so 1 0 0, 1, so ultimate result is 1 plus 1 0 1 1. So this is the for 2 4 bit, if we add in for 2 4 bit data, if we add it, so with the help of the repeat carry, so we are getting this result. So you have seen that from the first LSBP, if any carry is propagating, then we go to the next stage. After getting the generating the carry, from the second stage it will go to the third stage, and from the third stage it is going to the final. Okay, so carry is propagating after some time. So but some bit we are giving at the same time, all the bits data bit we are giving, so that means the sum expression we are getting at an instant, but for the final carry we have to wait now for the intermediate carry. So repeating. So if you see the block diagram of a 4-bit repeat carry adder, so 4 full adder we are connecting with each other, and C0 is the initial carry, A0, B0, these are the data bit, A1, B1, A2, B2. So these are the data bit, and S0 sum, S1, S2, S3, so these are the 4 sum expression, sum bit we are getting. This is the MSB, most significant bit, and this is the LSB. So now C1, C2, C3, these are the intermediate carry, and finally our C4 will be the final carry. So now what, when A0, A and B value we are giving at the same time, that means sum S0, S1, S2, S3, that expression, that value will get after one full adder delay. Suppose if I consider the 2 nanosecond delay of this full adder to all the 2 nanosecond, all the 2 nanosecond, all 2 nanosecond. But after giving the data inputs, we will get the sum expression after 2 nanosecond. But for the final C4 carry, we have to wait this 2 nanosecond plus 2 nanosecond plus 2 nanosecond plus 2, total 8 nanosecond. After 2 nanosecond to 8 nanosecond, we are get the final carry. So that means this type of repeat carry adder, so that's why the name is coming repeat carry adder. So the if it is a 64-bit adder, 64-bit data, 64-bit by 64-bit. So for the final carry, 64 into the delay of one full adder. We have to wait for that times. So in a first in world, in this world, so this 64, if it is considered 2 nanoseconds, so that will be 128 nanoseconds. It is a huge delay. It is not possible. So this type of work adder circuit is not suitable for a bigger circuits where the delay is very concerned, because the for the first response, if the delay is so much, so nobody will accept it. Okay, so we have to, so for that we load we will add in, so directly we can use the, so intermediate delay of the carry we can decrease in a carry look ahead. It is a very interesting topic also. So thank you.